Good afternoon. Continue for heat exchanger. We previously cover until exercise. And then we have done the exercise. So now heat exchanger effectiveness. The log mean temperature difference was used in the equation Q equal to VA delta PNN. Ln equal to log mean. This form is convenient when the inlet and outlet temperature of the two fluid unknown can be determined by a heat balance. However, when the temperature of the fluid within the exchanger are not known, and then that is to be used. A method called the heat exchanger effectiveness is used, which does not involve any of the outlet temperatures. The symbol is epsilon. The heat exchanger effectiveness is defined as the ratio of the actual rate of heat transfer in a given exchanger to the maximum possible amount of heat transfer if an infinite heat transfer area are available. The temperature profile for a counterflow heat exchanger is this figure. HI refers to T heat, T hot inlet. This one is T hot outlet, T cold inlet, T cold outlet. So CH, C hot is more than C cold. Heat balance for cold and hot fluid Q equal to mCpH. In the case PHI minus THO is equal to mCp So Cp here is different. This depend on the fluid inside the heat exchanger. So TCO minus TCI. Effectiveness if the cold or fluid hot fluid is the minimum. So called epsilon CH, okay. CH, C hot THI minus THO over C cold over THI minus TCI equal to C max over C min. But if the hot is the minimum, later we have an example. So if it's hot is the minimum, CC divided by CH equal to C max. So in this case, C max, you see here, C max here, THI minus THO over C min THI minus TCI. So if it's hot is the minimum, so C max TCO minus TCI divided by C min THI minus TCI. In both equations, the denominator is the same, and the numerator that gives the actual heat transfer. So if you see here, the denominator is actually have the same expression. The changes is on the top or numerator. So Q equal to epsilon C min THI minus TCI. For single pass counterflow exchanger, epsilon equal to this equation. Define NTU as the number of transfer units, so NTU equal to UA over C min. Both equations have been plotted in graphical form. This is how you identify the epsilon or Higgs exchanger effectiveness. So for counter flow or the ferrule flow or core flow, sorry, core counter, core counter or core flow. What is a parallel? So do you determine the number of NTU? Yes. Then determine the value for epsilon. NTU equal to UA over C min. Example. Water flowing at a rate of 0.667 kg per second enters a counter current. Core current. This is a core current. Core flow. Core current. Heat exchanger at 0.08 Kelvin is lifted by an oil stream entering at 383 Kelvin at a rate of 2.85 kg per second. With CP refer to viscosity. The overall U equal to 300 watt per meter square Kelvin. And the area equal to 15 meters square. Calculate the heat transfer rate and the exit water temperature. Assuming that the exit water temperature is about 370 Kelvin, the CP for water at an average temperature of 239 Kelvin is 4.192. Refer to the appendix. Then MCPH equal to CH, the 2.8. So CH equal to, refer to the oil, 2.85, 1.89, multiply with 103. So 1.85, rate, MCP, 1.89, and 103. So the CP for the water is equal to A, 2 dash 5. This is appendix A, number 2. And MCPC, C refer to the coal. Okay, equal to C min. So how do they identify which one is C min, which one is C coal? Oh, sorry, C max. The value of C, in this case, CH is high, 5287. So it doesn't, it's possible that if CH has lower value than CC, then C min is could be hot. So CC is the new, so C min over C max to 0.519. So NTU equal to UA over C min, so U 300 and 15 2796, which is this value. Okay, using figure 16.3-2a. See, this one is 1.6. 1.6. This is a counter pattern. And 6 is here. It's here. Is it counter pattern? At least counter pattern in. And in here. Then what else? So C-bin over C-max is 0.1. So 0.519, 0.5. No? Yeah. How much? 0.71. Yeah, repeat. 0.6, 0.7. Ah. Mm. Okay. So GQ equal to okay, the is equal to temperature. Equal to epsilon C min THI minus TCI. Get this value for the heat transfer rate. Then Q equal to 148 equal to 2796. This is for the yes, mean PCO minus 308. Is something for PCO. So for this value, they referring to this equation. This one is based on the Q. So to exit temperature is 361.3 Kelvin. Okay. Now it's a design double pipe heat exchanger. After fermentation, a mixture of ethanol and water is sent to a small distillation column. Okay, there's some mistake. This one is actually like a single three and H. Okay. That's on the book. Refer to page 679 or 680. This value here is actually 10 to the 3, not 103. Okay. So to this double pipe is changing temperature, page 682. After fermentation, a mixture of ethanol and water is sent to a small distillation column at the top of the distillation column on 95% concentration at 65. DVC is produced at a flow rate of 3.5 kg per second. Your job is to design a double pipe heat exchanger that will cool the 95% temperature to 40 degrees C by using cooling water that is available at 10 degrees C, and after temperature of cooling water of 55 degrees C. When only use schedule 40, do not do viscosity correction for heat or transformation, and the 95% solution will be pumped to the inside pipe. Alright. So it's a double pipe situation. Vertical in, vertical out, vertical in, vertical out. Step 1. Complete the energy balance and calculate the amount of cooling water. Given an average heat capacity of the 95% ethanol solution of 2.6 kilojoule per kg Kelvin, then the heat loss by the 95% ethanol would be Q equal to mCp delta T equal to 3.5 kg per second. 2.6 kg per 1 kg per second is equal to the ethanol flow rate. Yes. 2.5 is the CP, delta T is 65 inlet. 40 outlet. So the purpose of the heat exchanger is to cool the ethanol. So from here, Q is for ethanol is 2275.5. So assuming the system is adiabatic, then all the heat loss from the 95% ethanol solution will be gained by the cooling water. Thus, the mass flow rate of cooling water is equal to since the Q is the same for ethanol and the water, so MCW, which is equal to mass of flow rate of cooling water, Q is the same. Divided by CP for water is 4.181, but this value is strictly based on the appendix A. A2. Yes, A2. And the temperature difference for the water, when we get MCP is 1.209 kg per second, where the average heat capacity of the water is 4.181 kilojoule per kg Kelvin. As shown in appendix A. Oh, there's A.2-5. That is step 1. Step 2, calculate inner tube diameter and velocity. Given an average density of the 95% ethanol solution of 8.16 kg per meter cube and estimating the inner tube velocity at 1 meter per second. To facilitate turbulence, the inner tube cross-sectional area and diameter are so area, okay, using this equation and over rho of V, 3.5 is the so inner tube refer to the ethanol. Okay. And divide by rho for ethanol at 116. For 1 meter per second velocity. 1 meter per second, I think they assume it the moment. Yes, they assume it at the moment, 1 meter per second. Then we get 4.289 times 10 to the power negative 3 meter square. 1 meter per second. Okay. The diameter D equal to square root for ACS. ACS is equal to cross section. So for cross section, divide by pi. So for 1 meter per second, you get a 74 mm diameter. But for 74 mm diameter, there is no 74 mm diameter for standard pipe or standard tube. Eh, sudah pindah. Kini roti. Interesting. Ito pa. Sudah tahu. It's okay. But it's available in appendix in the end of the book. Looking at appendix 8.5, 8.5-1, assuming the schedule 45 will suffice. The minimum nominal pipe size is 3 inches. With this pipe choice, the inner diameter area is 77.92 millimeter. Of with cross section 4.769 times 10 to the power negative 3 meter square, which is slightly larger than 34 mm required above. So we will have to calculate the velocity given the pipe size chosen. So in this case, we determine the 34 mm. This is value for estimation. We don't know the velocity. So we assume this area, sorry, velocity 1 meter per second. Get the area, determine the diameter. So the diameter is approximate. No, we cannot use this diameter because there is no data in schedule 40 appendix 5 A5. So the closest is 77.92 mm. So we choose the closest. Then using the new information, which is 77.92, we calculate, get the actual velocity. So 4.76 times 10 to the power negative 3 the square. This is equal to appendix A5-1. Step 3. Choose an outer tube diameter and calculate velocity. Logically, the outer pipe must have a larger diameter than the inside pipe. Looking at appendix F5-1 and assuming schedule 40 pipe will suffice, the next largest pipe will be 3.5 inch. which is true. Schedule 40 with inside emitter 90.12 mm and outside emitter of 1.6 mm. However, this would only give a difference of 1 mm between the outer emitter of the inside part to the inside emitter of the outside part. The estimated choice is for 4 inches with inside emitter of 102 and outside emitter of 114.3 mm. Okay, so for 3 inches, what will happen? So if you choose if you choose 3.5, so previously for this inside pipe, it's 3 inches. So now we need to design the outside pipe because it's double effect. So for the inside pipe, if we choose 3 inches, also 3.5 inches, yes, the 3 inches can go inside the 3.5, but the area for heat transfer is very small. You see here, it's only 1 mm. 1 mm. So in this case, we need to make it bigger, the area between the inside pipe and the outside pipe. So we choose 44 inches, schedule 40 with inside emitter 102, outside emitter 1143 mm. Therefore, the cross-sectional area available for flow in the annulus is, we calculate using this equation. So a cross section outside. So pi over 4 DIO refer to 10T of the inside pipe minus 88.9 is the inside pipe, but outside diameter we get 2.012 negative 3 meters square. From this area, the calculated flow rate of the cooling water rho equal to 996. So 996 is referred to appendix A2, A2. We get 2.103. The velocity of water, this is talking about outside pipe. So water flowing is 0.603 meter per second. Yeah. When the velocity is lower than 1 meter per second, we will assume that we obtain turbulence, which enhance heat transfer. Right. Calculate the step 4. Calculate the inside heat transfer coefficient from equation 15.3-5. So, so this velocity, this is for the cooling water. So this velocity is for the ethanol solution. So bear in mind we have two pipe. One, the small pipe is inside a bigger pipe. So inside the small pipe is ethanol. Inside the bigger pipe is the cooling water. So the viscosity thermal step 4, the viscosity thermal conductivity of the 95% ethanol solution is 9.72 times 10 of -4. kg per meter square, meter second, and 0.175 watt per meter Kelvin, respectively. Thus, determine the Reynolds number. So Reynolds number D is here inside. Okay. So D here refer to the inside diameter for the inside pipe, meaning it's for the ethanol. So 077.92 mm, 0.7 meter per second refer to the volume, velocity for the ethanol. Rho refer to the density of the ethanol divided by viscosity. The mean viscosity. Oh yeah, because what 684 viscosity of the ethanol is 9.72. So 9.72. So we get the Reynolds number. Now it's Prandtl number. Cp mu over K. K is 0.175. Mu 9.72. Cp is 2.6. Cp bagi. Cp bagi juga. No, Cp is 2.6. That one is page 683. We get 14.041. So H, the heat transfer coefficient for the inside pipe is, using this equation, mu water over apa ya? Mu B over mu W is equal to 1. Yeah. Then we get 966. So all the value is available in here or here. Cp. Step 5. Calculate the outside heat transfer coefficient from equation 15.3-7. Before using equation 15.3-7, we need to calculate the average cooling water temperature and the equivalent diameter of the annular space. So T average, this is for the water, the bigger part. So T average refer to the T average for the cooling water. So we get 33.5 D. Equivalent diameter DE is DIO minus DO. So 102 is the inside diameter for the big pipe, and 8.9 is the outside diameter for the small pipe. Then we get 0.0134 meter or 33.4 millimeter. Now we can use the simplified equation for water to calculate the outside diameter. Okay, so the HO refer to heat transfer coefficient for the outside part or bigger part, which contain water. So this is the equation. B is from here. B is from the step 2. So this V is referred to V for the cooling water, not for the ethanol. What else? 32.5 is the average. Okay, that's all. H naught is 2348.4. Step 6. Step 6. Okay, calculate the outside overall heat transfer coefficient. This is just the sum of the resistance at this point falling coefficient table 16.4-1 could be added for completeness, but this will be not for the example. So meaning there are no falling occurs in this double pipe section along with the connection to the scheduled body pipe. The heat transfer of interest in this design problem is the convection that occurs between the fluids. Due to sagging problem, we will limit the pipe length to 6 meter. Sagging meaning it's bending, and make bend in the pipe to get the necessary area needed for the design. In addition, we need to calculate the surface area where heat transfer occurs. This area is different from the cross-sectional area. We needed to calculate the velocity. So LP refer to the length of the pipe, the maximum length of the pipe to avoid bending. A naught here refer to the uh, so A naught here refer to the outside diameter for the inside pipe. So pi 0.8889 meter multiplied by 6 meter. This is talking about the inside pipe. AI equal to pi di and p. So di here refer to the inside diameter of the small pipe inside the pipe that carry or transfer the ethanol. The other is what is so now we can sum the resistance and calculate the heat overall heat transfer coefficient R equal to this is the resistance 1 over HI plus 1 over HOAO. AI and AO, this is both is referring to the small pipe, the inside pipe. UO, this is the overall heat transfer coefficient equal to 1 over R. AO here refer to this AO. Oh, refer to this AO. So we get value AO equal to 675.5. Step 7, calculate the area needed for heat transfer and the number of bend needed. Since we will design the exchanger in a counter current fashion, we must calculate the log mean temperature difference. This log mean temperature difference. So delta 1 refer to the 65 minus 55. Delta 2 is 40 minus 10. Okay. So delta T log mean temperature delta T2 minus delta T1 is okay. This is the delta TLM equivalent or to Kelvin. Now with the delta TLM, we will calculate the heat transfer area needed. So here equal to UOHE E area delta TLM. So we need to find the heat exchanger area. So H E area equal to this expression, we get 18.49 meter square. Yeah? So this is the overall, so this is the total heat. Again, We are limited to 6-meter long pipe, and thus we may not have enough area to satisfy the required area needed for heat transfer. 18 hole, 39 meter space, so we may need to bend the pipe. Because we, to avoid the sagging, the number of bend needed is equal to the total area needed for total heat transfer divided by the total the surface area of the 1/6 meter pipe chosen diameter. So in this case, N bend, and because N bend equal to HE 18.49 divided by AO. So AO refer to the inside pipe. So in this case now, inside pipe need to bend. So how many bend? 11 bend. Thus we will need 11 bend to get the necessary area needed to accomplish the thermal design. As stated in the example heading, this is a simplified thermal design. There is much more to consider, such as the pressure drop, before the tourism can be accomplished. Thank you. We